In question 10, the equation of a curve is such that the double derivative d square y upon dx square is 6x square minus 4x cube. The curve has a stationary point at minus 1, comma 9 upon 2. In the first part, we have to determine the nature of the stationary point at minus 1, comma 9 upon 2. So for the nature, we'll substitute the value of x into the double derivative. And if it is greater than 0, it will be a minimum point. And if it is less than 0, it will be a maximum point. So substituting x equals to minus 1, we will get 6 into minus 1 whole squared into minus 1 whole cube. So this will become a plus 1, and minus 4 upon minus 1 will make it a 6 plus 4. As this is greater than 0, this means it will be a minimum point. Now in part B, we have to find the equation of the curve. To do this, first we will integrate it to get the expression for dy dx, and then we'll integrate it again to get the expression in terms of y. So now integrating d square y upon d square x. So this is 6x square minus 4 upon x cube. Integrating this, we'll get dy by dx, and this will become 6x cube upon 3. And to integrate 4 upon x cube, first of all, we'll write the x cube in the numerator. So we'll write it as minus 4x to the power minus 3. So integrating minus 4x to the power minus 3, the power will increase by 1 and it will become a minus 2, and we'll divide by minus 2 and we'll add a plus c. We can simplify this to write it as 2x cube plus, so this will become a minus, minus will become a plus. 4 divided by 2 is 2, so this will be 2 upon x squared plus c is equals to dy upon dx. Now, as the stationary point, the coordinate was minus 1, comma 9 upon 2, and at the stationary point, the dy dx is 0, so we can write this as 0 over here and put the value of x is minus 1 whole cube plus 2 upon minus 1 whole squared plus c. So 0 will be equals to minus 2 plus 2 upon minus 1 whole squared will be positive 1. So this will be 2 plus c. So minus 2 plus 2 is 0. So in this case, c will be equals to 0. Now, once we have the value of c as 0, now we can integrate this expression again and get rid of the value of c. So first we'll write that dy dx will be is equals to 2x cube plus 2x to the power minus 2. Now integrating both the sides, we'll get y is equals to, so this will increase the power by 1. This will become 2x4 upon 4. Increasing the power by 1, this will become a minus 2 plus 1 will become a minus 1, and we'll divide by minus 1 and we'll add a plus c. So y will be is equals to 1 upon 2 x to the power 4 minus 2x to the power minus 1 plus c. Now to find the value of c, we'll substitute the points that were given, and the point was minus 1, comma 9 upon 2. So in place of y, we'll write 9 upon 2 is equals to minus 1 upon 2 into minus 1 to the power 4 minus, so we can write this x power minus 1 as 2 upon x and substitute minus 1 over here plus c. Solving this, we'll get 9 upon 2 is equals to 1 upon 2. So minus 1 to the power 4 will become a plus 1, and this will become a plus 2 plus c. So we'll write it as 9 upon 2 minus 1 upon 2 minus 2 is equals to c. 9 upon 2 minus 1 upon 2 is 8 upon 2, which is 4, and 4 minus 2 will be equals to c, which is equals to 2. So once we have the value of c as 2, the final equation will be y equals to 1 upon 2 x to the power 4 minus 2 upon x plus 2. In part C, it is asking us to show that the curve has no other stationary points. So to show that, first of all, we'll look at the expression for dy dx, which was 2x cubed plus 2 upon x squared. So we had dy dx is equals to 2x cubed plus 2 upon x squared. Now for a curve to have a stationary point, it means the dy dx will be equals to 0. So we'll put it equals to 0 and try and find the values of x. So taking the LCM, we'll get 2x to the power 5 plus 2 upon x squared equals to 0. Cross multiplying, this will become 2x to the power 5 is equals to minus 2. So we have taken this 2 on the other side, and so 2x power 5 will be equals to -2, or x powered 5 will be equals to -1. Now, if it even take the root 5 of -1, the value of x will still be a -1, which means that there is no other stationary point on the curve.